These are the discoveries that changed what scientists thought they knew about the universe, and every single one of them points toward the same unsettling pattern. The deeper we look into space, the less familiar it becomes. 95% of everything that exists is made of something we still cannot see, cannot touch, and cannot fully explain. And that number alone should stop you in your tracks before we even get started. If you're new here, stick around and hit subscribe, because we're about to walk through the strangest, best documented discoveries in modern astronomy, from black holes we've actually photographed, to a visitor from another star system, to a radio signal nobody has ever been able to explain, and none of it is science fiction. Every fact in this video comes from peer-reviewed research, NASA data, and confirmed observations from some of the most advanced instruments ever built. Let's get into it. We'll start with the number that quietly undoes almost everything you were taught to picture when you imagine the universe. When scientists look at all the stars, all the planets, all the galaxies, every telescope image ever captured, every atom in your body and mine, they are looking at roughly 5% of what's actually out there. NASA's own research, built on years of data from the Planck satellite, puts ordinary matter at about 5% of the total content of the cosmos. Dark matter accounts for around 27%, and dark energy makes up the remaining 68%. Before the 1930s, when dark matter was first proposed, that 5% wasn't just what scientists could see, it was assumed to be everything. The whole universe, as far as anyone knew, was made of stars and gas and light, full stop. Nobody had a reason to think otherwise, because nobody had a reason to look for anything else. Then astronomers started noticing that galaxies were spinning wrong. Stars near the outer edges of galaxies were moving far too fast to stay in orbit, based on the visible mass that was supposedly holding them there. By the laws of gravity, as they were understood at the time, those outer stars should have been flung off into space entirely, the same way a rock on a string flies away the instant you spin it too fast without enough force holding it in place. But they weren't flying off. Something invisible was providing the extra gravitational pull needed to keep those galaxies intact and spinning the way they do. And that something eventually got the name dark matter, not because scientists know what it's made of, but because it doesn't interact with light in any way we've ever been able to detect. It doesn't glow, it doesn't block starlight passing behind it, it doesn't reflect anything back to our instruments. We only know it's there because of what it visibly does to everything around it. The way you'd know wind was blowing through a room even with your eyes closed, just by watching the curtains move. And here's where it gets even stranger, because dark matter isn't even the biggest mystery on this list. Dark energy is. Dark energy is the name given to whatever is causing the universe to expand. And not just expand, but expand faster and faster as time goes on. For a long time, physicists assumed the expansion of the universe should be slowing down, the same way a ball thrown into the air eventually loses speed and falls back to Earth, pulled down by gravity the whole way. Instead, observations from the Hubble Space Telescope showed the exact opposite happening. About 7.5 billion years ago, something shifted, and the rate at which galaxies are flying apart from each other started accelerating rather than slowing down. Whatever is doing that is called dark energy, and it makes up roughly 68% of the entire universe, according to NASA's own findings. Meaning the single largest ingredient in all of existence is something researchers still cannot identify, describe, or replicate in a laboratory. Those precise percentages, 5% ordinary matter, roughly 27% dark matter, and around 68% dark energy, come from one of the most careful censuses ever taken of the universe's contents, built on data from NASA's WMAP satellite, which spent years mapping tiny variations in the temperature of the cosmic microwave background, the faint afterglow radiation left over from the Big Bang itself. Those variations are genuinely tiny. One patch of sky reading a temperature of roughly 2.7251 degrees above absolute zero, another reading just 2.7249 degrees. A difference so small, it's hard to imagine it mattering at all, and yet those minuscule fluctuations, first detected by NASA's earlier COBE satellite back in 1992, turned out to be the imprint of the very earliest structure in the universe, the seeds that would eventually grow into every galaxy, star, and planet that exists today. WMAP's data also supported one of the most extraordinary claims in modern physics. that the universe underwent an initial period of expansion so explosive it grew by more than a trillion times its original size, in less than a trillionth of a second, a concept researchers call inflation, and one we'll come back to in more detail later in this video. Sit with that for a second. The category of stuff we don't understand at all is not a small footnote tucked into the back pages of cosmology. It is the majority stakeholder in reality itself. Everything we've ever built a working theory around, from atoms to stars to planets to black holes, is a minority position in the actual makeup of the universe. And that's the theme running underneath every single discovery we're about to cover today. Each time astronomers get a better tool, a sharper telescope, a more sensitive detector, the universe doesn't get simpler, it gets stranger, it gets bigger, and it gets a little more humbling. Take black holes, for instance. For most of the 20th century, black holes were mathematical predictions, the kind of thing that fell directly out of Einstein's equations for general relativity, but had never actually been observed with anyone's own eyes. Scientists inferred their existence indirectly by watching stars orbit something invisible at high speeds, or by tracking X-rays thrown off by matter falling into an unseen, incredibly dense source. Nobody had a picture, nobody had proof they could look at and simply point to. That changed on April 10, 2019, when the Event Horizon Telescope collaboration released the first image ever taken of a black hole's event horizon, and the science world hasn't looked the same since. The target was a supermassive black hole sitting at the center of a galaxy called M87, roughly 55 million light-years from Earth. To even attempt something this ambitious, researchers had to build something that had never existed before in human history, a telescope effectively the size of the entire planet. They didn't do it by constructing one enormous dish somewhere, because no single dish could ever be built that large. Instead, they linked together 8 separate radio observatories scattered across the globe, from Hawaii to Spain to Chile to the South Pole, and synchronized their observations down to the level of atomic clocks, so precise that every single telescope was, in effect, listening to the same instant in time. Together, those 8 instruments functioned as one single virtual telescope, with the resolving power of an instrument the size of Earth itself. That is the level of precision it took just to photograph something 55 million light-years away. What came back was an image that looked almost hand-drawn, a glowing ring of superheated gas circling an unmistakable dark void at the center, the black hole's shadow, caused by light bending around it and disappearing entirely at the edge of its gravitational pull. The black hole itself turned out to be 6.5 billion times more massive than our Sun, a number so large it barely means anything until you try to picture it. An object with the mass of 6.5 billion suns compressed down into a single point in space. Paul T.P. Ho, a board member of the Event Horizon Telescope project, said that once the team was confident they had genuinely imaged the black hole's shadow, they compared it against decades of theoretical models built on warped space and superheated matter, and the real image matched those predictions with remarkable precision. It was one of those rare moments in science where a century-old theory met direct photographic proof and simply held up under pressure. 3 years later, the same team pulled off something arguably even harder. On May 12, 2022, they released the first image of Sagittarius A star, the supermassive black hole sitting at the exact center of our own galaxy, the Milky Way. It's much closer than M87, only about 27,000 light-years away, which sounds close until you remember that's still roughly 158,000 trillion miles. Despite being nearer, imaging it was actually more difficult, because clouds of gas and dust sitting between Earth and the galactic center scatter the radio waves the telescope relies on, blurring the picture the same way thick fog blurs a photograph taken through it. Sagittarius A star is also far smaller than M87's black hole, only about 4 million solar masses instead of 6.5 billion, meaning it consumes matter more slowly and glows far more faintly as a result. Astrophysicist Ryan Hickox, who wasn't even part of the project, called the achievement astounding and said he suspected most of his colleagues across astronomy shared that same sense of stunned gratitude when the image was finally released. For the first time in human history, we had direct visual evidence, not indirect inference, not orbital math scrawled across a chalkboard, but an actual photograph of the invisible giant sitting at the heart of our own galactic neighborhood. But photographing black holes wasn't the only way scientists confirmed they existed. 7 years before that first image, on September 14, 2015, at exactly 5:51 in the morning Eastern Time, 2 detectors on opposite sides of the United States picked up something no instrument had ever recorded before in the history of physics. One detector sat in Livingston, Louisiana. The other sat in Hanford, Washington. Both are part of a project called LIGO, the Laser Interferometer Gravitational Wave Observatory, and what they detected that morning was a ripple in the fabric of space-time itself, a gravitational wave, exactly as Einstein had predicted 100 years earlier in his theory of general relativity, back when he had no possible way of testing whether it was true. The wave had been produced in the final fraction of a second before 2 black holes, one about 36 times the mass of our Sun, and the other about 29 times, spiraled into each other and merged into a single, larger black hole of roughly 62 solar masses. Do the math on those numbers and something doesn't quite add up. 36 plus 29 should equal 65, not 62. That missing mass, the equivalent of about 3 entire suns, wasn't lost anywhere. It was converted directly into pure energy and radiated outward across the universe as gravitational waves, the exact same kind LIGO detected here on Earth, more than 1 billion light-years away from where the actual collision had happened. Scientists later confirmed those waves traveled at the precise speed of light, another checkmark in Einstein's favor, a full century after he first wrote the theory down on paper, with no telescope, no detector, and no way on Earth to prove it. Each of LIGO's 2 L-shaped detectors stretches about 4 kilometers along each arm, using split beams of laser light that travel back and forth between precisely positioned mirrors, with researchers measuring the distance between those mirrors closely enough to catch the almost impossibly tiny amount by which a passing gravitational wave stretches and compresses the fabric of space itself as it rolls through, according to MIT researchers who worked on the original detection. That single detection opened up an entirely new field almost overnight: gravitational wave astronomy. Essentially, a brand new sense for observing the universe that has nothing whatsoever to do with light. Since 2015, researchers have detected the mergers of black holes, the collisions of neutron stars, and events that stretch the very definition of what we thought empty space was even capable of doing. Space isn't a static, silent backdrop anymore, the way it might have felt in old textbook diagrams. It's something that can ripple, stretch, and vibrate, and we now have instruments sensitive enough to feel that happen from distances the human mind can barely process. By the early observing runs after that first detection, LIGO and its partner detector Virgo in Italy had already confirmed additional black hole mergers and the first ever detected collision between 2 neutron stars, and the pace of detections has only accelerated since, opening up window after window onto a universe that spends far more time in violent motion than anyone assumed before 2015. Now here's where things take an even stranger turn, because even with all of this progress, one of the most basic questions in all of cosmology still doesn't have an agreed-upon answer. How fast is the universe actually expanding? This might sound like something scientists nailed down decades ago and moved on from, but it hasn't been settled, not even close, and the disagreement has a name now: the Hubble tension. When astronomers calculate the universe's expansion rate using data from the early universe, specifically the cosmic microwave background, the faint leftover radiation from the Big Bang itself, they consistently get a number around 67 kilometers per second per megaparsec. But when they calculate that exact same number using local, present-day observations, things like pulsating stars called Cepheid variables and distant supernovae, they get a noticeably higher number instead, closer to 73 kilometers per second per megaparsec. That gap between 67 and 73 might look small, written out on paper, practically rounding error territory to an outsider. But in cosmology, it's enormous, and it has resisted every single attempt to explain it away as a simple measurement error. Multiple independent research teams, using entirely different methods, entirely different instruments, and entirely different assumptions, keep landing on the same discrepancy over and over again. Some scientists think this points to a genuine flaw hiding somewhere in our standard model of cosmology. Maybe there's an unknown particle we haven't accounted for yet. Maybe dark energy isn't actually constant the way physicists have long assumed it to be. Maybe gravity itself behaves slightly differently than expected once you zoom out to truly cosmic scales. Nobody knows for certain yet. What we do know is that the two most rigorous, most carefully checked methods available for measuring the exact same number keep disagreeing with each other, and that disagreement has only grown more statistically significant as the data has improved over the years, not less. Usually in science, better data quietly resolves a conflict like this one. Here, better data has made the mystery harder and harder to dismiss with each passing year, and researchers, as recently as 2026, have continued publishing ultra-precise measurements, confirming the tension is real, ruling out simple calibration errors as the culprit, and describing it as a possible sign that our current model of the cosmos is missing something fundamental. As if that weren't enough uncertainty for one universe to be sitting on, a completely separate mystery showed up the moment humanity's newest space telescope switched on for the very first time. The James Webb Space Telescope launched on Christmas Day 2021, built specifically to peer further back into the early universe than any instrument before it, catching light that had been traveling toward us since almost the very beginning of time. Astronomers had built careful predictions ahead of time for what they expected to find out there. Galaxies that should have still been small, faint, and only loosely formed, given how little time had passed since the Big Bang for anything larger to come together. Instead, almost as soon as the telescope opened its eyes on the sky, researchers started spotting big, bright, surprisingly mature-looking galaxies scattered everywhere throughout the early universe, in numbers and sizes that didn't line up with the models at all. One of the more striking individual finds came in early 2025, when researchers discovered a massive galaxy, complete with a fully formed spiral structure, nicknamed the Big Wheel, that existed within the first 2 billion years of the universe's entire history. A fully organized spiral galaxy, the kind of structure that typically takes many billions of years of gradual, patient assembly to form, showing up far earlier than anyone expected it could. Researcher Themia Nanayakara of Swinburne University of Technology in Australia, one of the scientists who worked on the discovery, noted that what made it so interesting wasn't just that it was big, but that it had already developed that clean, beautiful spiral shape at such an early point in cosmic history. Other teams studying the broader pattern have echoed the same confusion, noting that astronomers are seeing this kind of thing far more often than the standard models predicted, describing objects that were supposed to be rare turning up again and again across the JUIC's field of view. Some of these early galaxies appear to hold over 1 million times the mass of our Sun in stars, having somehow assembled that much mass in only a few 100 million years after the Big Bang, a cosmic eye blink by any reasonable standard. Researcher Sandro Chwarowski, whose work has focused directly on these unexpectedly massive early galaxies, summed up the confusion plainly, noting that these objects are supposed to be a rarity in the early universe, yet astronomers keep seeing more and more of them anyway, prompting the obvious question of what exactly is going on out there. This isn't a fringe theory floating around the edges of astrophysics either. It has become one of the most actively debated open problems in the field, spawning a wave of published research trying to figure out whether the issue lies with our fundamental model of the universe itself, or simply with our more localized models of how quickly stars and galaxies are capable of forming and growing once conditions are right. Some researchers have proposed that early galaxies may have gone through unusually rapid, intense bursts of star formation, essentially acting as extreme star factories capable of building up mass far faster than our models of typical galaxy growth ever accounted for, using observations of galaxies with unusually warm dust as supporting evidence for that idea. Whether that fully explains what JUIC keeps finding, or whether it points to something deeper still needing to be worked out, remains an open and actively contested question. But either way, the pattern holds firm across the entire field so far. Every leap forward in observational power keeps forcing scientists to revise their picture of the early universe upward in scale and complexity, never downward. The unexpectedly massive early galaxies weren't even the strangest thing the James Webb Space Telescope turned up once it started scanning the early universe. Almost from its very first data release in the summer of 2022, a completely different kind of object began showing up in nearly every single image the telescope captured. small, compact, unusually red points of light that quickly earned the nickname Little Red Dots. The objects were formally named in a March 2024 paper led by astronomer Jorit Mathi and colleagues, though by the summer of 2023, astronomers had already identified a consistent set of shared traits among them. They were small and tightly compact. They showed a strange, distinctive shape in their light spectrum that researchers described as V-shaped, and they showed signs of extremely fast-moving hydrogen gas. According to researchers who have tracked the population since, these objects show up in large numbers starting around 600 million years after the Big Bang, and then, strangely, largely vanish from the historical record of the universe by roughly 1.6 to 2 billion years after it, present in enormous numbers for a relatively narrow window of cosmic time, and then gone. At first, the implications seem to strain the standard model of cosmology even further than the oversized early galaxies already had. If the little red dots were genuinely as massive as some initial calculations suggested, it implied there were simply more supermassive black holes populating the early universe, and considerably more massive ones than the standard cosmological model predicted should have had time to form that early in cosmic history. Some astronomers began describing the situation using the same phrase that had already been circulating around the earlier galaxy puzzle, warning that duist might have effectively broken cosmology as scientists understood it. Multiple competing explanations were floated to account for the little red dots, ranging from heavily dust-obscured, intensely star-forming galaxies to extremely compact clusters of stars, to genuine supermassive black holes actively feeding on surrounding gas and dust. Two major research breakthroughs in 2024 started narrowing the field considerably. Researchers studying the little red dot population for signs of dust, the kind that would be expected to re-radiate all the energy it absorbed back out as detectable far-infrared light if dust were truly behind the object's unusual red coloring, kept coming up empty in survey after survey, findings that effectively ruled out entire categories of dust-based explanations. That left researchers focusing more heavily on the idea that at least a significant portion of the little red dot population represents genuine, actively growing black holes, but caught in an unusual, extreme phase of growth. In 2024, JUST directly observed one such black hole, dating from roughly 1.5 billion years after the Big Bang, actively pulling in material at an estimated 40 times the theoretical limit at which radiation pressure from a feeding black hole should normally choke off its own further growth, a limit astronomers call the Eddington limit. If earlier, even more distant black holes were feeding at similarly extreme, limit-shattering rates, it would help explain how objects that massive managed to form so early, without necessarily requiring cosmology itself to be wrong, simply requiring black holes capable of growing far faster than anyone previously modeled. Then, in a study presented at the American Astronomical Society meeting in January of 2026, researchers from the Center for Astrophysics at Harvard and Smithsonian proposed a genuinely striking alternative explanation for at least some of the population, that certain little red dots might not be black holes surrounded by galaxies at all, but rather a completely new category of object entirely, gigantic, short-lived supermassive stars, potentially as much as 1 million times the mass of our own Sun, essentially a missing evolutionary link representing the exact process by which the universe's very first supermassive black holes originally formed. And in June of 2026, researchers studying an especially useful little red dot, named GLIMPSE 17775, magnified and made easier to study thanks to the gravitational lensing effect of a foreground galaxy cluster sitting directly between it and Earth, gathered the deepest, most detailed spectrum of light ever collected from one of these objects, and found more than 40 separate spectral lines, all pointing consistently toward what researchers have started calling a black hole star, a rapidly feeding, growing supermassive black hole wrapped in a dense cocoon of partially ionized gas. According to the research team behind that study, no previous little red dot observation had ever produced this much consistent supporting evidence in one place, and the findings suggest the earlier, more alarming claims about broken cosmology may have resulted less from an actual crack in our understanding of the universe, and more from earlier observations simply not being sharp enough yet to properly reveal what these strange, fleeting, reddish points of light in the early universe actually are. As is so often the case throughout this entire subject, the mystery didn't get simpler as astronomers studied it more closely. It got more specific, more strange, and considerably more interesting. While all of this was unfolding in the world of black holes and cosmic expansion, something else showed up that nobody was expecting at all, and it came from far closer to home than any distant galaxy. On October 19, 2017, a telescope in Hawaii called Pan-STARRS 1 picked up a faint, fast-moving streak of light crossing the sky. A postdoctoral researcher named Robert Werrick spotted it the next morning and compared it against images taken the day before. The object was there in both frames, moving steadily across the sky at a pace that immediately caught the attention of anyone watching closely. Within days, astronomers realized this wasn't a normal comet or asteroid behaving the way normal comets and asteroids do. Its orbit was hyperbolic, meaning it wasn't looping around our sun the way everything native to our solar system does, held in place by the sun's gravity in a long, repeating path. It was simply passing through, on a trajectory that would eventually send it flying back out into interstellar space, never to return again. It was named Oumuamua, a Hawaiian word that roughly translates to a messenger from afar arriving first. And it earned that name honestly, because it was the first confirmed object ever detected that originated outside our solar system entirely. Before you even factor in what it actually looked like, that alone made it historic. Humanity's first documented visitor from another star system, something astronomers had theorized about for decades without ever actually catching one in the act. But what it looked like only deepened the mystery surrounding it. Oumuamua was elongated, up to about 400 meters long, roughly a quarter mile, and shaped like a cigar, or possibly a flattened pancake, somewhere around 10 times longer than it was wide. Nothing in our own solar system, no asteroid, no comet ever observed before or since, comes anywhere close to that kind of extreme, stretched-out shape. NASA's own researchers described it as shaped like nothing we'd ever seen before in our own solar system neighborhood. It had been drifting silently through interstellar space for what researchers estimate to be millions of years before it ever crossed paths with our sun, tumbling end over end through the emptiness between stars long before human civilization existed to eventually notice it. Once it did cross into our solar system, astronomers only had a matter of months to study it before it faded out of observable range entirely, moving too fast and receding too quickly from Earth for any extended, leisurely observation campaign. During that narrow window, something odd turned up in the data that researchers weren't expecting. The object was accelerating slightly faster than gravity alone should have allowed, the kind of subtle extra thrust you'd typically expect from a comet venting gas as it warms up near a star, creating a tiny but measurable push. But when researchers checked for the telltale signs of a comet doing exactly that, a glowing tail, a visible trail of dust and gas streaming behind it, there wasn't one to be found. Deep imaging turned up essentially no dust around the object at all, so the extra acceleration was real, and it was measured carefully. But the explanation that normally accounts for that kind of behavior simply wasn't present in the data. To this day, that detail hasn't been fully resolved to everyone's satisfaction, and it's a large part of why Oumuamua remains one of the most debated single objects in modern astronomy. It rotated once every 7.34 hours as it tumbled end over end through our solar system, and then it kept going, and we will likely never get another close look at it again for the rest of human history. If interstellar visitors sound rare, they are. In the years since Oumuamua, astronomers have confirmed only a small handful of other objects of its kind, starting with a comet named Borisov, discovered in 2019, 2 years after Oumuamua's own brief and startling appearance. Researchers now estimate that an object like Oumuamua likely passes through the inner solar system roughly once a year on average. We've simply been missing them for essentially the entire history of astronomy, because until relatively recently, nothing we had built was sensitive enough to see them coming in time to notice. An object like Oumuamua naturally brings up the bigger question sitting quietly underneath almost every conversation about the cosmos, the question of whether we are actually alone out here. And that question has its own famous formal name in science, the Fermi paradox, and it comes with a very specific origin story. In the summer of 1950, Physicist Enrico Fermi, the same Enrico Fermi who had helped pioneer the first self-sustained nuclear chain reaction and later won the Nobel Prize in Physics, was having lunch with a group of fellow scientists at the Los Alamos National Laboratory in New Mexico. The conversation had drifted toward extraterrestrial life and the flying saucer reports that were popular in the culture at the time. Then, seemingly out of nowhere, in the middle of a completely unrelated conversation, Fermi asked a simple, blunt question that stopped the table cold. Exactly how he phrased it has been remembered slightly differently by each of the people who were actually there that day. Physicist Edward Teller recalled it as, "Where are they?" Herbert York remembered it as, "Don't you ever wonder where everybody is?" And Emil Konopinski recalled it as, "But where is everybody?" According to Teller's own account, the result of Fermi's question was general laughter around the table, because despite the question coming completely out of the blue, everybody there understood instantly that he was talking about intelligent life somewhere out among the stars. The question was deceptively powerful, and it still is more than 70 years later. Fermi understood just how old the universe actually is, and he understood that if advanced civilizations existed elsewhere in our galaxy, some of them could plausibly be millions or even billions of years older than humanity itself. Even accounting for relatively slow methods of interstellar travel, a civilization with that kind of head start, that kind of accumulated time, could theoretically have spread itself across enormous portions of the galaxy by now, filling it the way a slow but steady population eventually fills every available space, given enough generations. So, if intelligent life is genuinely common out there, the paradox asks, where is everybody? The universe appears vast enough and old enough to contain countless potentially habitable worlds, and yet to this day, humanity has found no confirmed evidence whatsoever of any other civilization, anywhere, at any point in its search. Explanations for the silence have piled up over the decades. Life itself may simply be rarer than we assume. Intelligence may seldom evolve even where life does take hold. Civilizations may tend to destroy themselves before they ever manage to spread very far. The distances between stars may simply be too vast for any realistic method of travel, or alien societies may communicate using methods entirely unfamiliar to us, or may be actively and deliberately avoiding contact for reasons we can't begin to guess. At present, none of these explanations has been confirmed over the others. The silence, as researchers now put it, simply remains. And that silence very nearly got broken, or at least appeared to, on the night of August 15, 1977, at Ohio State University's Big Ear Radio Telescope, a massive metal structure, roughly the size of 3 football fields laid end to end, spread across roughly 3 acres of grassy farmland near Delaware, Ohio, on the campus of Ohio Wesleyan University. The observatory had spent years quietly conducting the search for extraterrestrial intelligence, one of the longest-running SETI projects ever undertaken, running continuously from 1973 all the way to 1995. On that particular night, the telescope picked up a strikingly intense, narrow radio transmission from somewhere in the direction of the constellation Sagittarius, lasting a total of 72 seconds. Nobody noticed it happen in real time, because the observatory relied on volunteer astronomers to review the printouts by hand the following morning. That volunteer, astronomer Jerry Eman, sat down the next day to review the previous night's data the way he always did, checking a simple line printer readout where each line represented 10 seconds of averaged radio energy across 50 separate frequency channels. And there it was, a signal so unusually strong compared to everything around it on the page that Eamon circled the sequence of characters in red ink and, almost without thinking about it, wrote a single word in the margin beside it. Wow. The printout characters themselves read 6EQJ5, an encoded representation of the signal's rising and falling strength as it passed through the telescope's field of view, climbing in intensity for 36 seconds and then fading back down over the following 36, exactly the pattern you'd expect from a genuine celestial source drifting through a fixed antenna beam as the Earth rotated beneath it. The signal arrived close to a frequency of 1,420 MHz, the so-called hydrogen line, a wavelength associated with the most common element in the universe, and one long theorized by SETI researchers as a logical, universal frequency that any advanced civilization might choose to broadcast on, precisely because any other civilization capable of radio astronomy would likely already know its significance too. Follow-up checks of satellite records at the time confirmed that no known satellites or spacecraft were anywhere near that position in the sky when the signal was recorded. And then, just as suddenly as it had appeared, it was gone. Despite dozens upon dozens of follow-up observations pointed at that exact same patch of sky in the years afterward, using instruments considerably more sensitive than the original Big Ear telescope, the signal has never been detected again. Not once, not by anyone. To this day, nearly 50 years later, nobody can say for certain what caused it. It remains, according to researchers who have studied it since, one of the very few unexplained signals SETI has ever recorded in its entire history. A 72-second mystery that arrived once, matched almost exactly what scientists had theorized an alien transmission might look like, and then vanished into permanent silence. From here, the story shifts from strange signals and unexplained visitors toward the strange worlds orbiting other stars entirely. And exoplanet research over the past 2 decades has uncovered environments that sound more like something pulled out of myth than out of an ordinary physics textbook. Take WASP-76b, a gas giant located roughly 640 light-years away in the constellation Pisces. It's tidally locked to its star, meaning one side of the planet permanently faces its sun, while the other is locked in permanent, unending night, the same way one side of our own moon always faces Earth and the other never does. On the daylight side, temperatures climb above 2400 degrees Celsius, more than 4300 degrees Fahrenheit, hot enough to vaporize metal outright, turning solid iron directly into gas. Strong winds carry that vaporized iron across the planet toward the cooler night side, where temperatures drop enough for the iron vapor to condense back into liquid droplets, and then it falls as rain, molten iron rain, falling out of the sky on the dark side of a planet 640 light-years from wherever you happen to be sitting right now. Astronomer David Ehrenreich, who led the research team that confirmed this using an instrument called Espresso on the Very Large Telescope in Chile, put it about as plainly as anyone possibly could. One could say that this planet gets rainy in the evening, except it rains iron. Then there's 55 Cancri E, sitting about 41 light-years from Earth, roughly twice the size of our own planet, but nearly 8 times its mass. It completes a full orbit around its star in under 18 hours, which tells you almost everything you need to know about just how close it sits to its sun, and surface temperatures are thought to exceed 2000 degrees Celsius, hot enough to keep rock in a molten, liquid state across much of its surface, more ocean of lava than solid ground. Because the planet appears to contain an unusually high proportion of carbon relative to its total mass, some early models proposed that under the crushing pressure inside the planet, that carbon could be compressed into diamond, essentially describing a world with a diamond-studded interior. That theory has been challenged and revised since it was first proposed, and more recent research has cast real doubt on exactly how much of the planet is diamond versus other carbon-based material. But the fact that scientists were seriously modeling a planet as a potential diamond world, orbiting a star not entirely unlike our own sun, tells you just how far exoplanet science has already pushed the boundaries of what counts as scientifically plausible. And then there's HD 1189733b, a gas giant about 64 light-years from Earth, with a deep, striking blue color that from a distance looks almost like a twin of our own planet's oceans, reflected back at us across the void. It isn't. That blue tint actually comes from silicate particles suspended high in its atmosphere, scattering light the same way certain particles scatter blue light here on Earth. And this planet experiences winds recorded at roughly 8,700 kilometers per hour, close to 5,400 miles per hour, more than 20 times faster than the strongest hurricane ever measured anywhere on our own planet. Those winds are strong enough to drive the planet's suspended silicate particles sideways through the atmosphere as something far closer to shards of glass than to gentle rainfall. From orbit, it would look like a beautiful blue marble. Up close, it's one of the single most hostile environments ever modeled by astronomers working in this field. A few other worlds astronomers have catalogued round out just how varied this category of object turns out to be. TRES 2b, identified in 2011, holds the distinction of being the darkest exoplanet ever discovered, reflecting less than 1% of the light that hits it, making it darker than a lump of coal, for reasons researchers still haven't fully pinned down. And WASP 121b, a scorching hot Jupiter roughly 850 light-years away, orbits so close to its star that researchers describe it as nearly being torn apart by tidal forces, with an upper atmosphere heated past 2500 degrees Celsius, and a spectroscopic signature revealing exotic compounds like vanadium oxide and titanium oxide drifting through its skies, chemicals that create entire layers where temperature actually increases the higher up through the atmosphere you go, the reverse of how temperature normally behaves on a planet like Earth. Every one of these worlds is a reminder that planet is a far broader, stranger category than the 8 familiar examples in our own solar system ever really prepared any of us for. But not every exoplanet discovery reads like a horror story. Some of the most exciting findings of the last decade have pointed in the opposite direction entirely, toward worlds that might actually resemble something closer to home. On February 22, 2017, NASA announced one of the most significant exoplanet discoveries in its history. A single small, dim, ultra-cool dwarf star named TRAPPIST-1, sitting about 40 light-years from Earth, was found to host not 1, not 2, but 7 Earth-sized planets. More Earth-sized worlds discovered orbiting a single star than had ever been found anywhere else before. 3 of those 7 worlds sit within the star's habitable zone, the region around a star where temperatures could theoretically allow liquid water to exist on a planet's surface, the single most basic requirement scientists look for when searching for potentially life-friendly conditions elsewhere in the galaxy. The discovery itself unfolded in stages. Astronomers using the ground-based TRAPPIST telescope in Chile first spotted 3 planets around the star back in 2015, publishing that initial finding in 2016. Then, using NASA's Spitzer Space Telescope for an intense 21-day continuous observation campaign, researchers discovered that what they thought was a single additional planet was actually 4 separate worlds, bringing the total up to a stunning 7 Earth-sized planets, circling one small star. The entire system is so compact that all 7 planets, all 7 of them together, could comfortably fit within the orbit of Mercury around our own Sun, arranged more like a miniature version of Jupiter and its many moons than like a scaled-down solar system. TRAPPIST-1 itself is barely larger than Jupiter, only about 12% the diameter of our own Sun and less than 9% of its mass, meaning this compact little red dwarf hosts an entire family of Earth-sized worlds tucked in astonishingly close around it. Since the initial 2017 announcement, follow-up research using the Hubble Space Telescope and, more recently, the James Webb Space Telescope has continued studying the system closely, confirming the planets are likely rocky in composition and even suggesting, based on the star's own composition and behavior, that the system itself could be almost twice as old as our own solar system. In March of 2023, the James Webb Space Telescope delivered its first real science results from the system, examining the innermost world, TRAPPIST-1b, and finding little evidence of any meaningful atmosphere surrounding it, an early but important data point as researchers work their way outward through the remaining 6 planets, several of which sit in far more temperate positions than that scorched innermost world. Astronomer Michael Gillon, who led the team behind the original discovery, described the stakes plainly, calling it the first real opportunity to characterize the atmosphere of a genuinely Earth-sized planet sitting inside a star's habitable zone, something that had simply never been within scientific reach before. Let's bring this back down to something that sounds almost too extreme to possibly be real, but is fully documented and precisely measured: neutron stars. When a massive star runs out of fuel and collapses in on itself in a supernova explosion, what's sometimes left behind isn't a black hole, but something almost as strange in its own right: a neutron star. These objects are typically only about 20 kilometers across, roughly 12 miles, small enough that one could theoretically fit inside the boundaries of a mid-sized city if you dropped it there. And yet packed into that 20-kilometer sphere is a mass around 1.5 times that of our entire Sun. The density involved is genuinely difficult to describe using ordinary, everyday terms. Different research sources put a single teaspoon of neutron star material anywhere from millions to billions of tons, depending on the specific neutron star being studied and the model used to estimate it. But every single estimate, across every reputable source, describes something that sounds physically impossible right up until you remember it's actually been measured, not merely imagined by science fiction writers. Neutron stars also spin, and some of them spin at speeds that are genuinely hard for the human mind to process properly. The fastest confirmed pulsar, a rotating neutron star named PSR J1748-2446 AD, rotates 716 times every single second. That's not a theoretical estimate pulled from a model. That number comes from directly counting radio pulses as they arrive at a telescope on Earth and timing them precisely against an atomic clock, one of the cleanest, most exact measurements in all of astrophysics. Picture something with more mass packed into it than our entire sun, spinning more than 700 times a second, and you start to genuinely understand why astronomers describe these objects the way they do, not as strange exceptions to the rules of physics, but as places where the rules of physics get pushed to their absolute limit, and somehow, against every intuition, still hold together without tearing themselves apart. Not every strange world out there even bothers to orbit a star at all, and that turns out to be one of the more unsettling discoveries to come out of recent years. Scientists call them rogue planets, or sometimes free-floating planets, worlds that drift through the galaxy completely untethered from any sun, wandering through the dark on their own. Astronomers first detected hints of these objects back in the year 2000, and since then, researchers have used tools like gravitational microlensing, a technique that watches for the way a massive object's gravity briefly bends and magnifies the light of a distant star passing behind it, to confirm hundreds of rogue planet candidates scattered across our galaxy. Based on the numbers detected so far, some scientists now estimate there could be as many as 2 trillion rogue planets wandering through the Milky Way alone, potentially outnumbering ordinary, star-bound planets by a factor of roughly 6 to 1. The James Webb Space Telescope has only deepened that mystery further. When astronomers pointed JOST toward the Orion Nebula, one of the most active star-forming regions close to our own solar system, they found more than 500 Jupiter-mass, planet-like objects simply floating free within the surveyed region, with roughly 9% of them paired up in orbiting binary systems, a category astronomers have started calling Jupiter-mass binary objects, or JUMBOs for short. That's an entirely new class of object nobody had catalogued in these numbers before. 2 planet-sized worlds locked in orbit around each other, with no star anywhere nearby holding either of them in place. Then, in a separate 2024 survey of a star-forming region called NGC 1333, roughly 960 light-years away in the Perseus molecular cloud, JOST turned up 6 more rogue planets forming through a process astronomers had only ever associated with the birth of actual stars, condensing directly out of collapsing clouds of gas and dust, rather than being built up gradually inside a disk of leftover material around a young star, the way planets in our own solar system formed. Astrophysicist Ray Jayawardhana of Johns Hopkins University, one of the researchers behind that discovery, explained that the team was essentially testing the absolute lower limit of how light an object can be and still form the way a star does. One of those 6 rogue worlds even turned up with its own surrounding disk of gas and dust, hinting that it might be in the process of forming its own miniature moons, a planet with no star of its own, somehow managing to build a small family of satellites regardless. Researchers studying that same NGC 1333 region found that despite JOST's ability to detect objects considerably smaller, none of the rogue worlds they found came in below roughly 5 times the mass of Jupiter, suggesting that limit may represent a genuine physical cutoff, the smallest an object can be, and still form the way an actual star does, with anything lighter presumably needing to build up gradually inside a young star's leftover disk instead. And the team estimated that objects like these accounted for as much as 10% of everything found within the surveyed star cluster. And these worlds aren't always just drifting passively either. In 2025, researchers using the European Southern Observatory's Very Large Telescope found evidence of a free-floating world roughly 620 light-years away that appeared to be actively feeding, pulling in gas and dust from its immediate surroundings, and growing at an estimated rate of 6 billion tons of material every single second, a kind of solitary, starless growth spurt astronomers had never directly observed before. It raises a genuinely strange question that astronomers are still actively debating, somewhere out there right now, floating silently through the dark, with no sun to warm it, and no star system to belong to. There may be more planets than there are stars in the entire galaxy. Some of the strangest, most violent objects in the universe, though, don't wander quietly at all. They announce themselves. Magnetars are a rare and extreme type of neutron star, and according to NASA, they carry the strongest magnetic fields of any known object in the universe, up to 1,000 times more intense than an already powerful ordinary neutron star, and up to 10 trillion times stronger than a simple refrigerator magnet hanging on your kitchen wall. Researchers have described the scale of that magnetism in genuinely strange terms, a field powerful enough to wipe the data off a credit card from roughly the distance of the Moon. Only about 30 magnetars have been identified anywhere in the Milky Way so far, making them exceptionally rare even among the already exotic category of neutron stars, with catalogued examples including the well-studied SGR 1900+14 and the considerably younger Swift J1818.0-6007, discovered in 2020 and thought to be one of the youngest magnetars known. Because a magnetar's crust is under constant, immense strain from its own magnetic field, that field can suddenly twist, tangle, and violently snap back into a more stable configuration, a process that shakes the entire neutron star the way an earthquake shakes solid ground, and astronomers have started calling these events starquakes for exactly that reason. When one of these ruptures happens, it releases a burst of energy in the form of X-rays and gamma rays, some small, some catastrophically large. On December 27, 2004, a magnetar called SGR 1806-20, sitting roughly on the far side of our own galaxy, unleashed a giant flare so powerful that it partially ionized Earth's upper atmosphere from tens of thousands of light-years away and briefly saturated the detectors on NASA's own satellites, designed specifically to observe events like it. According to researchers who studied the event, in a mere fifth of a second, that single flare released as much energy as our own sun produces over roughly 250,000 years. Then, on April 15, 2020, an even more tightly documented event occurred. A pulse of X-rays and gamma rays, lasting just 140 milliseconds, swept across our entire solar system, later confirmed as a giant flare erupting from a magnetar in a nearby galaxy. According to NASA's own findings, that discovery confirmed a long-held suspicion among astronomers that at least some of the mysterious gamma-ray bursts detected almost daily across the sky, cosmic eruptions astronomers had puzzled over for years, are in fact powerful flares thrown off by magnetars relatively close to our cosmic neighborhood, rather than more distant, exotic events entirely. Gamma-ray bursts themselves are widely described by researchers as the single most powerful class of explosion known to occur anywhere in the universe, capable of being detected across billions of light-years of empty space, and astronomers now understand that some of the shorter ones, lasting less than about 2 seconds, come specifically from a pair of orbiting neutron stars, finally spiraling together and merging. A scenario confirmed directly back in 2017, when a gamma-ray burst was observed, arriving right alongside a burst of gravitational waves produced by exactly that kind of merger, happening 130 million light-years away. Sometimes the strangeness isn't a violent flash lasting milliseconds, but a slow, months-long transformation happening right in front of astronomers watching from Earth with the naked eye. Betelgeuse, the bright reddish star marking the shoulder of the constellation Orion, has been one of the most closely watched stars in the night sky for well over a century. And for good reason. It's a massive, aging red supergiant, and it is, at some undetermined point in the future, expected to end its life in a supernova explosion. So when Betelgeuse suddenly and dramatically began losing its brightness starting in October of 2019, the astronomical world, and a huge chunk of the general public along with it, immediately started asking the obvious question: was this it? Was Earth's most famous nearby supergiant finally about to go? The dimming was real, and it was significant. Betelgeuse had ranked among the 10 brightest stars visible in Earth's night sky, but by the end of December 2019, it had slipped all the way down to 21st place, fading steadily at a documented rate of roughly 1/100th of a magnitude per day. It kept fading until it reached its faintest point on February 9, 2020, the deepest dip in its brightness recorded in at least 8 years of careful observation, before beginning an unexpectedly rapid recovery, brightening back at roughly twice the speed it had originally dimmed, and by April 19th of that same year, it had actually become even brighter than it had been the day before the whole event began. Astronomers ended up calling the whole 6-month episode the Great Dimming, and it triggered a genuinely enormous worldwide observation campaign, with researchers scrambling to point every instrument they could at the star before any potential explosion, just in case. As tempting as the supernova explanation was for headline writers at the time, and plenty of outlets ran with it anyway, the scientific consensus that eventually emerged told a less explosive, but arguably even more fascinating story. Researchers combining spectroscopic data, direct imaging from instruments like the Very Large Telescope's interferometer, and years of careful photometric tracking determined that Betelgeuse had experienced a genuine surface mass ejection, essentially expelling a huge blob of its own outer material, equivalent to several times the mass of our Moon, out into space. That ejected material cooled as it drifted away from the star and condensed into an enormous cloud of dust, which then drifted directly into our line of sight and blocked a significant portion of the star's light from reaching Earth. The same basic principle as smoke passing in front of a lamp. Separate research pointed to an additional contributing factor as well, a large, unusually cool star spot forming on the star's surface, dropping its effective surface temperature by at least 170 degrees Kelvin at the peak of the dimming, compounding the effect of the dust cloud passing in front of it. As astronomers researching the event have since pointed out, there is no known precedent anywhere in the recorded history of supernova observations for this kind of dramatic dimming phase to precede an actual explosion, and nothing in current computer models of dying stars predicts it should happen that way either. Betelgeuse will explode eventually. That much is essentially certain given its size, mass, and stage of life. But the great dimming of 2019 and 2020, as dramatic and headline-grabbing as it was, turned out to be the star simply shedding a piece of itself, not announcing its final act. Radio telescopes, it turns out, have picked up more than just one unexplained signal over the decades. In 2007, astronomer Duncan Lorimer and his colleagues were combing back through archived data from Australia's Parkes Radio Telescope, originally collected years earlier for an entirely different pulsar survey, when they noticed something buried in the old records that nobody had caught the first time around. A burst of radio waves lasting only a few milliseconds, so intensely bright that it had actually saturated the telescope's detection equipment at the time it was recorded. What became known as the Lorimer burst, officially catalogued as FRB 010724, turned out to be the very first documented example of an entirely new class of cosmic event, the fast radio burst, or FRB. These bursts are exactly what the name suggests: extraordinarily bright flashes of radio waves lasting anywhere from a fraction of a millisecond up to a few dozen milliseconds at most, over almost before any instrument can properly register them, yet carrying enough energy packed into that brief window to be detected from across truly staggering cosmological distances. Distances research has since confirmed place their sources in distant galaxies far beyond our own. For years after that first discovery, fast radio bursts remained frustratingly rare and mysterious. A handful of one-off flashes scattered across the sky with seemingly no pattern and no repeat appearances. Then in 2016, researchers using the Arecibo Observatory in Puerto Rico discovered something that upended the entire picture. A previously catalogued burst, known as FRB 1201102, didn't just flash once and vanish the way earlier bursts had. It repeated, firing off burst after burst from the exact same point in the sky, proving conclusively that at least some fast radio bursts come from a source capable of surviving its own explosive outburst and firing again, rather than a single catastrophic, one-time event like a star's final collapse. Researchers were eventually able to trace that particular repeating source back to a small, dim dwarf galaxy, roughly 3 billion light-years away, undergoing an unusually high rate of star formation, hinting that its bursts were somehow connected to the life cycle of young, extreme stellar remnants. Then, in 2020, researchers uncovered something even stranger, a repeating burst designated FRB 1800916 that wasn't firing off randomly at all, but on a distinct, predictable 16-day rhythm, active for roughly 4 days at a stretch, and then falling completely silent for 12 days before starting the cycle all over again. As lead researcher Duncan Lorimer, the same astronomer behind the original 2007 discovery, put it at the time, there was nothing particularly unusual about this specific repeating source individually, meaning if this one displayed such a clean, predictable periodicity, other fast radio bursts likely have hidden rhythms of their own too, simply waiting to be found by researchers looking closely enough. One proposed explanation involves the source being paired with a companion object in a binary system, with the burst's radio signal periodically getting blocked or disrupted as the companion object's stellar wind sweeps across our line of sight, though that remains one hypothesis among many, rather than a settled answer. And in an especially striking twist, astronomers eventually caught an FRB-like pulse coming from a source right here inside our own Milky Way galaxy, traced directly to a known magnetar named SGR 1935+2154, offering the first solid, direct link between fast radio bursts and the same magnetically extreme neutron stars responsible for some of the giant flares and gamma-ray bursts covered earlier in this video. That detection came courtesy of the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, a wide-field radio telescope that has become one of the most productive fast radio burst hunting instruments in the world, part of the same broader push that has helped the total number of confirmed fast radio bursts climb into the many hundreds since Lorimer's original 2007 discovery. Researchers studying the field have been careful to note that this doesn't necessarily explain every single fast radio burst ever detected, with hundreds of confirmed sources now catalogued and dozens of competing theories still in circulation. But it was the first time scientists had a genuinely direct, close-up example to study, rather than a faint signal arriving from billions of light-years away, with no way to examine its source up close. Not every strange discovery of the last decade required a radio telescope pointed at some distant galaxy, either. Some of the strangest moments came from a spacecraft reaching out and physically touching an object right here in our own solar system's backyard. NASA's OSIRIS-REx spacecraft, launched in September of 2016, arrived at a small, potentially hazardous near-Earth asteroid named Bennu in December of 2018, and spent nearly 2 years carefully studying it from orbit before attempting to actually collect a physical sample of its surface. Based on everything the mission team had observed from a distance, they expected Bennu's surface to behave essentially like solid rock, firm enough that the spacecraft's sampling arm would simply tap the surface and bounce back with a small scoop of material, the same way you might expect a spacecraft to interact with, say, a boulder. On October 20, 2020, when OSIRIS-REx finally descended and made contact with the surface, that assumption fell apart almost instantly. Instead of meeting resistance, the spacecraft's sampling head sank roughly 1.5 feet straight into the asteroid within seconds, meeting almost no resistance at all. Mission scientists and engineers had braced themselves for something closer to a pogo stick bouncing off gravel. What they got instead was, in the words of Dante Lauretta, the mission's principal investigator, closer to jumping straight into a pit of plastic balls, the kind found in children's play areas. Had the spacecraft not immediately fired its thrusters to pull itself back away from the surface right after grabbing its sample, researchers later determined it likely would have kept sinking, potentially deep enough for the loosely bound material of the asteroid to swallow the spacecraft whole. It turned out Bennu's exterior was made up of particles so loosely packed and so lightly bound to one another that they behaved almost like a fluid rather than a solid surface at all, held together by little more than weak mutual gravity, the kind of structure scientists call a rubble pile asteroid. Researcher Kevin Walsh of the Southwest Research Institute, who studied the resulting data, explained that if Bennu had been solidly packed the way everyone originally assumed, it would essentially amount to solid rock, but instead, the team found enormous amounts of empty void space woven through the asteroid's surface material. OSIRIS-REx successfully carried its sample, roughly 250 grams of dust and rock, all the way back to Earth, touching down safely in the Utah desert on September 24, 2023. the largest sample returned from beyond the moon by any NASA mission since the days of the Apollo program. When scientists finally finished analyzing the material back on Earth, in 2025, they announced the sample contained water, amino acids, and nucleobases, the fundamental chemical building blocks associated with life as we understand it, preserved essentially untouched since the earliest days of our solar system's formation, roughly 4.5 billion years ago. A small, unassuming asteroid, expected to behave like an ordinary rock, turned out to have the texture of a children's ball pit and the chemistry of life's earliest ingredients tucked inside it, discovered only because a spacecraft reached out, touched it, and very nearly sank straight through. A reminder that even the objects in our own solar system we assume we understand best can still turn out to be built from something entirely unexpected the moment we actually make contact with them. Some of the strangest discoveries of all haven't required looking across billions of light years at all. They've been sitting quietly in our own solar system this entire time, hiding under a shell of ice, just a short hop away by cosmic standards. In 2005, NASA's Cassini spacecraft flew past a small, icy moon of Saturn called Enceladus, a moon barely 252 kilometers in radius, small enough that it seemed like an unlikely candidate for anything remarkable at all. Instead, Cassini's cameras caught something extraordinary, a towering plume of water vapor, ice particles, and organic molecules erupting directly from the moon's south polar region, shooting straight out into space. The discovery confirmed what scientists had only suspected, that hidden beneath Enceladus's frozen outer shell sits a genuine liquid water ocean, kept from freezing solid not by any warmth from the distant sun, but by the constant gravitational flexing and stretching the moon endures as it orbits Saturn, generating internal heat the same way repeatedly bending a paperclip back and forth generates heat at the bend. Cassini went on to fly directly through that plume 5 separate times, and onboard instruments confirmed the spray was made mostly of water, laced with trace amounts of carbon dioxide, ammonia, hydrogen, and even organic molecules including benzene compounds. The exact kind of chemical building blocks astrobiologists look for when searching for potentially habitable environments. Researchers studying the plume's composition later proposed that hot water rich in dissolved silica may be gushing up from Enceladus's rocky seafloor into the colder ocean above, cooling rapidly and forming tiny silica crystals that get carried upward and ultimately out through cracks in the icy crust. Evidence, according to scientists at NASA's Jet Propulsion Laboratory, of active hydrothermal activity happening on the ocean floor of a moon orbiting Saturn, a process not unlike the hydrothermal vents found deep in Earth's own oceans, environments here on Earth that are themselves teeming with life. Enceladus isn't alone in hiding an ocean, either. Jupiter's moon Europa has drawn similar fascination for decades, and evidence gathered from NASA's Galileo spacecraft, the Hubble Space Telescope, and large ground-based telescopes has repeatedly hinted at faint water plumes erupting from its surface as well, echoing what Cassini directly confirmed at Enceladus. Europa's ocean, if the current evidence holds up, is thought to run far deeper than Enceladus's, somewhere between 40 and 100 miles down, sitting beneath an icy shell and kept liquid by that same relentless gravitational flexing, this time from the tug-of-war between Europa, mighty Jupiter, and the moon's neighboring satellites. As Linnae Quick, a scientist working on NASA's Europa Clipper mission, has cautioned, though, Europa isn't necessarily going to turn out to be a simple copy of Enceladus, and researchers are careful to note that the plume evidence at Europa remains intriguing rather than fully confirmed, with some earlier detections later called into question after follow-up observations failed to reproduce them. NASA's Europa Clipper spacecraft is now underway specifically to settle the question, studying the moon from its deep interior down to its icy surface to determine whether the ingredients for life are genuinely present. And Europa and Enceladus aren't even the only candidates. Saturn's massive moon Titan is thought to potentially harbor its own subsurface water ocean beneath a surface famous for something even stranger still: lakes and rivers made not of water, but of liquid methane and ethane, the only other place in the solar system known to host stable liquid on its surface besides Earth itself. NASA has already approved a dedicated mission to go investigate Titan directly, a rotorcraft lander called Dragonfly, designed to fly repeatedly through Titan's thick atmosphere from one location to another, searching for the kind of prebiotic chemical processes that might hint at the raw ingredients of life forming under conditions utterly unlike anything found on Earth. It's a genuinely strange thing to sit with. Our own solar system, the one we assumed for centuries belonged entirely to Earth as far as liquid water and habitability were concerned, may actually be quietly hiding several more oceans than we ever accounted for, sealed away under ice, lit by nothing but starlight filtering through vacuum, and possibly churning with the same basic chemistry that gave rise to life here at home. Zoom back out from our own solar system, past our galaxy entirely, and the strangeness doesn't stop. It just gets bigger and stranger and considerably harder to visualize. Back in 1978, astronomers doing a careful survey of galaxy distributions in our corner of the universe noticed something odd. Galaxies, in the vicinity of our own Milky Way, all appeared to be drifting consistently toward one particular direction in the sky, as though something enormous and invisible were quietly pulling on all of them at once. Advances in X-ray astronomy roughly a decade later allowed astronomers to map the region more precisely, and what they found came to be called the Great Attractor, a region of intergalactic space, somewhere between roughly 150 and 250 million light-years from Earth, in the direction of the constellation Centaurus, that appears to be pulling our entire galaxy, along with thousands of others, toward it at a genuinely staggering speed, roughly 600 kilometers every single second. That's not a typo, and it's not a small number. Every second that passes, without you feeling a single thing, our galaxy moves another 600 kilometers closer to this mysterious point in space. For years, the Great Attractor was frustratingly difficult to study directly, because it happens to sit almost directly behind the dense, dusty plain of our own Milky Way galaxy, a region astronomers call the zone of avoidance, precisely because it's so hard to see through from our vantage point. Then, in September of 2014, a team of astronomers led by R. Brent Tully of the University of Hawaii finally mapped the full extent of the enormous structure surrounding it, using new techniques for tracking the actual motion of tens of thousands of galaxies rather than simply their positions. What they found and named was staggering in scale, a supercluster of galaxies, containing our own Milky Way as a fairly minor outlying member, spanning roughly 500 million light-years across, and holding the combined mass of about 100 million billion suns, spread across an estimated 100,000 individual galaxies. They named it Laniakea, a Hawaiian word meaning immense heaven, suggested by Hawaiian language professor Nawa'a Napoleon, and the name has stuck ever since. Tully described the achievement plainly at the time, saying the team had finally established the actual contours defining the supercluster of galaxies humanity gets to call home. Picture water flowing downhill into a valley, gathering speed as gravity pulls it toward the lowest point, and you have a rough sense of how galaxies behave within Laniakea's boundaries, all of them gradually flowing inward, guided by gravity, toward that same central basin where the Great Attractor sits. And even that staggering picture isn't the final word. Researchers studying the region have found that the Great Attractor itself, and the entire Laniakea supercluster surrounding it, appears to be slowly drifting toward an even larger, more distant concentration of mass, called the Shapley supercluster, suggesting the whole 100,000 galaxy structure we call home might itself be just one small current inside a far larger gravitational river we still don't fully understand the shape of. Every layer astronomers manage to peel back on this particular mystery reveals another layer sitting underneath it, superclusters flowing into larger superclusters, gravity quietly organizing hundreds of thousands of galaxies into rivers and valleys of cosmic structure that no single human observer will ever see the full shape of, only piece together, patiently, one careful measurement at a time. Even the outer edges of our own solar system, places astronomers once assumed were simply frozen, inactive, and geologically dead, turned out to be hiding their own share of surprises once we actually managed to send a spacecraft out to look. On July 14, 2015, after a journey of roughly 9.5 years and more than 3 billion miles, NASA's piano-sized New Horizons spacecraft swept past Pluto, giving humanity its first ever close, detailed look at the distant dwarf planet and its moons. For decades, Pluto had been little more than a fuzzy, ambiguous smudge even through the most powerful telescopes available, and researchers genuinely weren't sure what kind of world New Horizons would find when it finally arrived. A dead, ancient, unchanging chunk of ice, or something considerably more alive. What came back was the second option, emphatically. The most immediately famous feature New Horizons revealed was a massive, bright, heart-shaped region on Pluto's surface, roughly 1,000 miles wide, that quickly became the defining image of the entire mission. Its western lobe, known informally as Sputnik Planitia, turned out to be a vast glacier made of nitrogen, carbon monoxide, and methane ices, spread across roughly 1 million square miles, making it the largest known glacier anywhere in our solar system. According to researchers who have continued studying the New Horizons data in the years since, that nitrogen ice sheet isn't just sitting there frozen and static the way you might expect on a world where average temperatures hover around -229 degrees Celsius. It's actively churning, broken up into a mottled pattern of polygonal convective cells, typically somewhere between 10 and 30 miles across, formed as warmer nitrogen ice from deeper in the glacier slowly rises to the surface, while cooler surface ice sinks back down to take its place. Essentially the same basic convective process you'd see in a pot of water gently simmering on a stove, or, as scientists studying the feature have described it, something closer to an enormous, planet-sized lava lamp. Researchers estimate the surface ice in these cells is less than 1 million years old, a genuinely young age by planetary standards, meaning Pluto's icy heart is still actively resurfacing itself in real time, not preserving some ancient, unchanged landscape from billions of years ago. The heart-shaped glacier turned out to be more than just a striking visual detail, either. It appears to be gravitationally significant enough that it may have physically reoriented the entire dwarf planet over time, settling into a position that now sits almost directly opposite Pluto's largest moon, Charon. Beyond the glacier itself, New Horizons revealed mountain ranges built from water ice hard enough to hold their shape at Pluto's extreme temperatures, winding canyons, other nitrogen glaciers flowing down from surrounding highlands and carving valleys as they travel. Features that put Pluto in the same select company as Earth and Mars as one of the very few bodies in our solar system with actively flowing glaciers on its surface. The spacecraft also caught sight of what appear to be ice volcanoes, structures potentially spewing slush made mostly of water ice rather than molten rock, hinting at genuine ongoing geological activity happening on a small, distant world that scientists had largely written off as inert before the flyby. And looking back at Pluto's night side after the encounter, New Horizons captured an image of a hazy, layered atmosphere extending roughly 100 miles above the surface, faint blue in color, a detail described by mission co-investigator Michael Summers as nearly bringing the atmospheric science team to tears the moment they saw it. A tiny, distant, ice-covered world, 5 billion kilometers from home, turned out to be nowhere near as frozen and lifeless as everyone assumed. And in a very real sense, it's still teaching researchers new things to this day, years after the spacecraft itself has already moved on, continuing its own long journey out toward interstellar space, carrying with it a small canister of Clyde Tombaugh's ashes, the very astronomer who first discovered Pluto back in 1930, riding along on the spacecraft that finally gave humanity its first real look at the tiny, distant world he spent his life searching for. One more strange transformation worth mentioning is happening on a planet humans have been staring at through telescopes for centuries, close enough and bright enough that you don't need a space agency's budget to see it for yourself on a clear night. Jupiter's Great Red Spot, a swirling anticyclonic storm large enough to swallow the entire planet Earth, has been watched and measured by astronomers going back to the late 1800s, and for the entire span of that recorded history, it has been steadily, unmistakably shrinking. Historic observations from the late 19th century put the storm at roughly 25,500 miles across at its widest point, wide enough to fit 3 Earths side by side with room to spare. When NASA's Voyager 1 and Voyager 2 spacecraft flew past Jupiter in 1979, the storm had already contracted to about 14,500 miles across. By 1995, a Hubble Space Telescope photograph measured it at roughly 13,000 miles, and by 2009, it had shrunk further still, down to around 11,100 miles. Then, starting in 2012, amateur astronomers tracking the storm from backyard telescopes around the world noticed something researchers hadn't expected. The rate of shrinkage was speeding up. According to Amy Simon of NASA's Goddard Space Flight Center, who has led ongoing Hubble observations of the storm as part of a long-running project called the Outer Planets Atmospheres Legacy Program, which conducts annual observations of Jupiter and the other giant planets, specifically to track exactly this kind of long-term atmospheric change. The Great Red Spot's waistline has been shrinking by roughly 580 miles every single year since that acceleration began, and its shape has been steadily changing from an elongated oval into something closer to a simple circle. By 2014, Hubble measurements confirmed the storm had shrunk to approximately 10,250 miles across, the smallest diameter ever recorded in the storm's long observational history. Nobody currently knows exactly why. Simon and her research colleagues have observed that small eddies appear to be feeding into the storm from its surroundings, and have proposed that these smaller disturbances may be altering the internal dynamics and energy balance of the Great Red Spot in ways that are accelerating its long-term contraction, though the full mechanism remains an open, actively studied question. More recent research led by Simon has added another wrinkle to the puzzle as well, finding that even as the storm continues shrinking in width, it appears to be growing measurably taller, and that its long-term shrinkage hasn't been a perfectly smooth, one-directional process either, with the storm's total area apparently increasing again at least once somewhere along the way. As Simon herself put it, storms are dynamic, and that's exactly what researchers keep seeing when they study the Great Red Spot: constant change in its size, its shape, and the speed of the winds tearing through it. Nobody knows whether the shrinking will eventually stop, stabilize, reverse, or continue until the most famous storm in the solar system, a storm humans have been watching continuously since before the invention of the automobile, eventually disappears from Jupiter's face entirely, or simply settles into some new, stable shape and size that future generations of astronomers will spend their own careers trying to explain. Sometimes the strangest mystery isn't something astronomers have found, it's something they keep finding indirect evidence for without ever actually seeing it. Out beyond Neptune sits the Kuiper Belt, a vast, sparsely populated field of icy bodies drifting through the outer reaches of our solar system. And in 2014, researchers Chad Trujillo and Scott Shepard noticed something odd while studying the most distant objects out there. 13 of them shared a strange similarity in a specific, obscure feature of their orbits, one that shouldn't have lined up so neatly by pure chance. 2 years later, in 2016, Caltech astronomers Konstantin Batygin and Mike Brown took that observation further, identifying 6 extremely distant Kuiper Belt objects whose orbits weren't just similar in that one narrow respect, they were clustered together in physical space as well, all tilted in the same unusual direction relative to the rest of the solar system's orbital plane. The two astronomers calculated the odds of that kind of alignment happening purely by random chance at somewhere around 1 in 15,000, roughly 0.007%. That's the kind of number that makes scientists sit up and start looking for a cause, rather than simply chalking it up to coincidence. Batygin and Brown's proposed explanation was that a genuine, undiscovered planet sitting far beyond Neptune, somewhere between 5 and 10 times the mass of Earth, orbiting the Sun once every roughly 10,000 years, was using its gravity to herd those distant objects into their strange, aligned formation, the same way a shepherd's presence might keep a scattered flock moving in the same general direction without ever needing to touch each individual member of it. They ruled out the possibility that undiscovered smaller Kuiper Belt objects alone could account for the pattern, calculating that it would require the entire Kuiper Belt to hold roughly 100 times more mass than it's currently estimated to have. A genuine planet fit the data far better, and researchers have continued finding supporting threads in the years since, including mysterious, mismatched orbits belonging to a couple of specific distant objects nicknamed Sedna, discovered by Mike Brown himself back in 2003, and 2012 VP-113, announced by Trujillo and Shepard in 2014, orbits that Planet Nine's proposed gravity would neatly explain, according to Batygin and Brown's own modeling. But not everyone in the field is convinced, and that disagreement is exactly what makes this mystery worth including here. Some researchers studying the same distant Kuiper Belt population through independent surveys have found no clustering at all, once they carefully accounted for the direction their own telescopes happened to be pointed during observation, arguing the apparent alignment might simply be an artifact of where astronomers have historically looked, rather than a genuine pattern in the underlying objects themselves. Other physicists have proposed entirely different explanations for the same data without invoking a new planet at all, including modified theories of gravity that behave differently at the extreme faint edges of the solar system than standard Newtonian physics predicts. As of now, no telescope has ever directly photographed Planet 9, and researchers candidly acknowledge that if it exists, it would be faint enough and distant enough that spotting it directly remains a genuine technical challenge even for our most powerful instruments. Batygin has said that his favorite characteristic of the whole hypothesis is precisely that it's testable, that somewhere out there, a real photograph of a genuine ninth planet may eventually be possible, a prospect he's called absolutely electrifying. For now, though, the evidence remains indirect, a scattered pattern of icy, distant orbits pointing towards something we can infer but have never actually seen, sitting quietly in the dark at the edge of our own solar system, exactly the kind of unresolved mystery this entire video keeps returning to again and again. Zoom all the way back out to the largest scale imaginable, the entire observable universe itself. And there's one more strange, stubborn anomaly worth mentioning before we close things out. Scattered across the cosmic microwave background, that same faint afterglow of the Big Bang mentioned earlier in connection with both the Hubble tension and cosmic inflation, researchers expect to see a fairly uniform pattern of tiny temperature variations, the leftover imprint of minuscule density differences in the infant universe, differences of only about 1 part in 30,000, scattered evenly across the sky in every direction, but sitting in one particular patch of sky, first detected using data from NASA's WMAP satellite, and later confirmed independently by the European Space Agency's Planck satellite, is a region researchers simply call the cold spot, an area of the cosmic microwave background that reads notably unusually colder than anything else surrounding it. Standing out from the expected pattern at a level of statistical significance, researchers analyzing the Planck satellite data have measured at around 3 standard deviations, a level that's hard to wave away as ordinary noise, though not quite strong enough on its own to count as an ironclad, indisputable anomaly by the strictest standards physicists hold themselves to when deciding whether something genuinely breaks a model or simply sits at its statistical edge. For years, the leading explanation held that the cold spot was caused by light from the Big Bang's afterglow, traveling for billions of years directly through an enormous supervoid, a vast region of space containing far fewer galaxies than average, slowly losing energy as it passed through that emptiness and arriving at our telescopes measurably cooler as a result. In 2021, using the Dark Energy Survey and the Blanco telescope in Chile, researchers confirmed the existence of exactly this kind of enormous void sitting directly in the same patch of sky as the cold spot, an immense, sparsely populated region of the cosmic web named the Eridanus supervoid, among the largest such voids ever mapped. That confirmation might sound like it settled the matter, but researchers studying the data closely have pointed out that the physics doesn't add up quite as neatly as the simple explanation suggests. The supervoid, once its full size and depth were properly measured, doesn't appear to be quite large or quite empty enough, according to standard cosmological models, to fully account for just how cold that patch of sky actually reads. As astrophysicist Andras Kovac, one of the researchers behind the more recent measurements, has put it, having these two individually rare and unusual structures, the supervoid and the cold spot, line up together in the same place isn't, on its own, quite enough to scientifically prove one is causing the other. Some researchers have suggested the discrepancy might point towards something deeper still poorly understood about the true nature of dark energy itself, the same mysterious force that makes up the bulk of the universe and that we already met at the very start of this video. Whether the cold spot ultimately turns out to be an ordinary, if extreme, statistical fluke sitting by pure chance in front of a genuinely enormous void, or a real crack in our fundamental understanding of how the universe evolves on its largest possible scales, remains, like so much else covered here, a question our best instruments have narrowed down considerably without yet fully closing. And researchers on both sides of the debate agree that only deeper, more precise surveys of that same patch of sky will ultimately settle it, one way or the other. Every discovery covered so far in this video has involved something astronomers could eventually point an instrument at, however faint, however distant, however strange. But some of the most consequential ideas in modern cosmology exist right at the edge of what any instrument could ever directly confirm, and one of the strangest is the theory of cosmic inflation and the multiverse concept that grew directly out of it. In 1980, physicist Alan Guth, then working at MIT, proposed a theory to solve a problem that had been quietly nagging at cosmologists studying the standard Big Bang model. Why does the universe look so remarkably uniform and smooth in every direction we look, and why is its overall geometry so close to perfectly flat, when the ordinary physics of an expanding universe gave no obvious reason for either to be true? Guth's answer was cosmic inflation, the idea that for an almost unimaginably brief sliver of time, immediately after the universe's birth, less than a millionth of a trillionth of a second, some exotic form of matter or energy exerted a strange kind of gravitational repulsion instead of ordinary gravitational attraction, causing space itself to expand at an explosive, exponential rate before settling back down into the far more gradual expansion cosmologists had already been observing. The theory did more than patch over an awkward gap in the Big Bang model. It actually made testable predictions, and decades later, researchers studying the cosmic microwave background, the same faint afterglow of the Big Bang that plays a role in the Hubble tension debate covered earlier in this video, found patterns in its structure consistent with exactly the kind of rapid early expansion inflation predicted. But inflation carried an unexpected, almost unsettling consequence along with it. One that physicist André Linde, another major contributor to the theory, worked out in the years following Guth's original proposal. If inflation happened once, there's no obvious reason within the physics of the theory itself for it to have happened only once, or to have stopped absolutely everywhere at the same time. Linde proposed a refinement called eternal inflation, in which inflation continues forever across the broader fabric of space, constantly and randomly settling down into stable, non-inflating regions in some spots, while continuing to expand explosively everywhere else, endlessly spawning what researchers call bubble universes, or sometimes pocket universes, each one a fully separate region of space-time that stopped inflating and cooled down into something resembling an ordinary, stable universe, potentially with its own distinct laws of physics, entirely separate from our own. Under this picture, what we experience as the Big Bang wasn't necessarily the beginning of everything that exists. It may simply have been the moment our own particular bubble broke away from a much larger, eternally inflating background, stopped its runaway expansion, and began cooling into the universe we now observe, while inflation itself kept right on going elsewhere, indifferent to what happened inside our bubble, generating an effectively endless number of other bubbles doing the exact same thing. Alan Guth himself, decades after first proposing inflation, has said plainly that it's genuinely difficult to construct a working model of inflation that doesn't eventually lead to some version of a multiverse, a strange position for the original architect of the theory to find himself defending, having set out simply to explain the smoothness of one universe and ending up with a theoretical framework that keeps producing infinitely many of them instead. It's worth being honest about where this theory currently sits, because it isn't universally accepted the way, say, the detection of gravitational waves or the imaging of a black hole's shadow are. Researchers studying the multiverse concept have been candid that testing it directly, or even meaningfully calculating the odds of our particular universe existing among an infinite variety of others, runs into serious mathematical and philosophical difficulties that remain unresolved. Some physicists consider the broader multiverse implications of eternal inflation to be a natural, almost unavoidable mathematical consequence of a theory that has otherwise been remarkably successful at predicting features of our own universe. Others consider the multiverse itself to be a much more speculative extension, one that may not even be testable in principle, given that separate bubble universes, if they exist, would likely be forever cut off from any possible contact or observation from within our own. Guth himself has described inflation, in later reflections on his own theory, as something like a prequel to the Big Bang itself, setting up the conditions the more familiar, hot, expanding universe would eventually inherit. Either way, it stands as maybe the ultimate example of the pattern running through this entire video. A theory built to explain something relatively modest and well-grounded. The uniform smoothness of the universe we can actually observe ended up implying something almost too vast to properly comprehend. An unknown, possibly infinite number of other universes, sitting just outside anything we will likely ever be able to reach, measure, or confirm directly, forever, just past the edge of what our best instruments and our best mathematics can currently tell us for certain. Zoom back out one more time, because after covering supervoids tucked behind the cosmic microwave background, there's an even larger, even stranger patch of emptiness sitting closer to home in cosmic terms, one that astronomers found completely by accident back in 1981. Astronomer Robert Kirshner and his colleagues at the University of Michigan were working on something fairly routine at the time, measuring the redshifts of a large number of galaxies to help build an early three-dimensional map of the universe's large-scale structure. Redshift, in simple terms, measures how quickly something is moving away from us, and because the universe is expanding, the farther away a galaxy sits, the faster it's generally moving away, which means redshift can double as a rough measurement of distance. As Kirshner's team built out their map, galaxy by galaxy, something strange started to emerge in one particular region of sky, roughly 700 million light-years from Earth, sitting in the direction of the constellation Boötis. There was almost nothing there. Not literally nothing, but close enough that it startled the astronomers who found it. The region turned out to be a roughly spherical void, spanning about 330 million light-years across, large enough that our own Milky Way galaxy could be dropped into it billions of times over, without coming anywhere close to filling the space. Based on how densely galaxies are typically distributed throughout the rest of the universe, roughly one galaxy for every 10 million light-years or so, astronomers calculated that a region this size should contain something in the neighborhood of 2,000 galaxies. Instead, painstaking follow-up surveys conducted over more than a decade, adding new discoveries in 1987, 1988, 1989, and continuing through the late 1990s, turned up a grand total of just 60. It became known first as the Great Nothing, and later, more formally, as the Boötis Void, and it remains one of the largest known voids anywhere in the observable universe, with the Hercules supercluster, a genuinely massive concentration of galaxies in its own right, forming part of the void's near edge, a stark boundary between an area crowded with galaxies and one almost entirely without them. Astronomer Greg Aldering, one of the researchers who helped track down some of those sparse 60 galaxies, offered a genuinely unsettling way to think about the void's sheer scale, noting that if our own Milky Way happened to sit at the very center of the Boötis void, instead of where it actually is, humanity might not have even known other galaxies existed until sometime in the 1960s, simply because there would have been almost nothing nearby bright enough to notice with early telescopes. It's worth being clear about what the Boötis void actually represents, because it isn't evidence that something is broken in our understanding of the cosmos, quite the opposite. Astronomers now understand that voids like this one are simply the natural, expected gaps that form between the enormous, thread-like filaments of galaxies, making up what researchers call the cosmic web, the large-scale structure of the entire universe, arranged not randomly, but into clusters, filaments, and empty basins, the way soap bubbles arrange themselves into froth, with matter concentrated along the thin walls between bubbles and almost nothing filling the bubbles themselves. What makes the Boötis void worth pausing on isn't that it breaks the model, it's the sheer, almost incomprehensible scale of just how much genuinely empty space is woven through a universe that, from Earth, looks so densely packed with galaxies, stars, and light. It stands as maybe the starkest possible reminder that the universe isn't uniformly full of the things we spend most of our time studying. It's mostly emptiness, with matter clumped together in relatively thin, if spectacular, filaments running through an ocean of almost nothing at all. Let's close out with a discovery that doesn't require a telescope pointed outward at all, but rather a very small, very stubborn creature that scientists deliberately launched off our own planet just to see what would happen. In September of 2007, the European Space Agency's Photon M3 mission carried a payload into low Earth orbit, containing roughly 3,000 dehydrated tardigrades, tiny, 8-legged microscopic animals, commonly nicknamed water bears or moss piglets, rarely larger than 0.5 millimeter in length. Using a piece of hardware called the Biopan 6 platform, essentially a sealed cassette mounted to the outside of the spacecraft that could be opened briefly in orbit and then sealed shut again before re-entry, researchers directly exposed the tardigrades to the open vacuum of space itself for 10 full days, along with the full, unfiltered blast of cosmic radiation and, for some of the samples, direct solar ultraviolet light entirely unfiltered by any atmosphere, the same radiation Earth's own atmosphere normally absorbs long before it ever reaches the ground. Before launch, the tardigrades were dried down into a specialized, near-dormant survival state called a toon, in which the animals expel nearly all of the water from their bodies, curl into a tight, barrel-like shape, and drop their metabolic activity down to levels essentially too low to detect. A biological trick called cryptobiosis that tardigrades use here on Earth to survive extreme drought and other hostile conditions. When the spacecraft returned and researchers rehydrated the samples back on the ground, the results were remarkable. According to the researchers who ran the study, tardigrades exposed to the vacuum of space alone, shielded from direct solar radiation, showed essentially no drop in survival compared to a normal, unexposed control group. Even more strikingly, some of the tardigrades exposed to the combination of open space vacuum and the full, unfiltered solar radiation spectrum survived that ordeal as well, and went on to reproduce successfully once they were revived, becoming the first animal ever confirmed to survive that specific combination of stresses: full space vacuum, cosmic radiation, and direct solar ultraviolet light, all at once, published formally in the journal Current Biology in 2008. A separate tardigrade experiment flown in 2011 aboard the final flight of NASA's Space Shuttle program produced a similarly striking result, with researchers reporting that roughly 68% of the tardigrades involved survived their own trip to orbit and went on to give birth to normal offspring after returning home. It's a strange, almost comic note to end on in a video otherwise filled with black holes and gravitational waves and galaxies from the dawn of time. But it belongs here all the same, somewhere in the same universe, capable of producing magnetars, interstellar wanderers, and 100 trillion galaxies scattered across an ever-accelerating expanse of space. There's also a 0.5 millimeter long animal from our own planet's forests and mossy rooftops that can be dried out, launched into the vacuum of space, blasted with unfiltered solar radiation, and simply come back to life once you add water again. So far, everything we've covered has involved things you could, at least in principle, point a telescope at. But some of the strangest, best confirmed discoveries in modern physics don't require a telescope at all. They require nothing bigger than a single photon of light. And one of the strangest of all is quantum entanglement. The phenomenon itself was first seriously debated back in the 1930s, when Albert Einstein, of all people, argued against it, describing it dismissively as spooky action at a distance. The basic idea is this: when two particles become entangled, measuring a property of one of them instantly determines the corresponding property of the other, no matter how far apart the two particles happen to be, whether that's across a lab bench or, in principle, across opposite sides of the galaxy. Einstein found this deeply uncomfortable, because it seemed to require some kind of instantaneous influence passing between the two particles, faster than the speed of light, which his own theory of relativity flatly forbids. He believed quantum mechanics had to be incomplete, and that some hidden variable we simply hadn't discovered yet would eventually explain the correlation without breaking the cosmic speed limit. For decades, this stayed mostly a philosophical argument rather than a testable one, until physicist John Stuart Bell, working in the 1960s, devised a mathematical way to actually put the question to the test. Bell showed that if Einstein was right, and some local hidden variable was secretly coordinating the particle's behavior in advance, the results of certain experiments would fall within one range of statistical outcomes. But if quantum mechanics was correct instead, and the entanglement was genuinely as strange as it appeared, the results would fall outside that range entirely, violating what became known as a Bell inequality. It took until the 1970s and 1980s for physicist John Clauser to actually build an experiment capable of testing this directly, and when he ran it, the results clearly violated Bell's inequality, lining up with the predictions of quantum mechanics rather than Einstein's hidden variable theory. Physicist Alan Aspect later refined the experiment further, closing an important loophole by switching the measurement settings on the particles after they had already left their source, but before they reached the detectors, ensuring the particles couldn't have somehow communicated or coordinated their answers in advance through any conventional means. Physicist Anton Zeilinger pushed the research even further afterward, expanding the use of entangled particles and helping lay the groundwork for the field of quantum information science entirely. In October of 2022, all three of them, Aspect, Clauser, and Zeilinger, were jointly awarded the Nobel Prize in Physics for this exact body of work, decades after the experiments themselves were first carried out, for proving, about as conclusively as physics ever proves anything, that quantum mechanics is correct, and that Einstein's uncomfortable, spooky action at a distance isn't a flaw in the theory waiting to be patched out. It's simply how the universe actually behaves at its smallest scales, whether that makes intuitive sense to us or not. If quantum entanglement shows just how strange the universe gets at its smallest possible scale, humanity's own farthest-reaching object shows just how far we've physically managed to travel outward from home, even without ever leaving our own solar system's immediate neighborhood. Voyager 1, launched on September 5, 1977, sent out originally to explore Jupiter and Saturn, a mission nobody at the time expected would still be running and still making history, nearly half a century later. On August 25, 2012, Voyager 1 became the first human-made object in history to cross into interstellar space, passing beyond the heliopause, the outer boundary where the sun's magnetic field and solar wind finally give way entirely to the space between the stars. At the moment it crossed that boundary, Voyager 1 was roughly 11 billion miles from the Sun, about 122 astronomical units out, with 1 astronomical unit representing the average distance between the Earth and the Sun itself. Researchers confirmed the exact crossing date afterward by studying the spacecraft's instruments, which recorded a 1,000-fold drop in solar particles and a 9% jump in cosmic rays arriving from outside the solar system entirely, a clean, unmistakable signature of the moment Voyager 1 left the Sun's influence behind for good. Long before it ever reached interstellar space, Voyager 1 had already been quietly making history for decades. On February 17, 1998, it overtook an older NASA probe called Pioneer 10 to become the single most distant human-made object in existence, a title it has held ever since. And by 2004, both Voyager spacecraft had already traveled well beyond the orbit of Pluto, continuing outward long after their original mission to study Jupiter and Saturn had been completed and declared a success. Voyager 1 is still traveling today, moving away from us at roughly 38,000 miles per hour, and it remains, to this day, the single most distant human-made object in existence, along with its twin spacecraft Voyager 2, which crossed its own version of that same boundary in 2018. Both spacecraft continue sending back data about the previously unexplored region of space they're now passing through, a region no human instrument had ever directly sampled before either probe arrived there. It's worth pausing on just how strange that really is. Two machines built in the 1970s, using computing power that would look laughably primitive by today's standards, are still functioning, still communicating with Earth across a gap of many light hours, and are still teaching us new things about the boundary of our own solar system that no simulation or theoretical model could have told us on its own. So where does all of this leave us? We started with a number, 5%, the fraction of the universe made of anything we actually understand, anything we can build a working model of, touch, measure directly, or explain with genuine confidence. The other 95% is dark matter and dark energy, two forces that shape literally everything, from how galaxies hold their form to how fast the universe itself is flying apart, and neither one has a confirmed physical explanation. Even now, decades after both were first identified. We've photographed the shadows of black holes, so massive they warp light itself, once at the heart of a distant galaxy 55 million light-years away, and once at the center of our own galaxy, 27,000 light-years from where you're sitting right now watching this. We've detected ripples in space-time crossing over 1 billion light-years to register as barely a whisper on instruments built with unimaginable precision, and confirmed that this newly discovered sense for observing the universe keeps turning up violent, hidden events happening constantly all around us, completely invisible to ordinary light. We've measured the universe's expansion rate 2 completely different ways and gotten 2 different, well-documented, repeatedly confirmed answers. A conflict that's only gotten sharper with better data instead of fading quietly away the way most scientific disagreements eventually do. Our newest telescope looked back toward the beginning of time itself and found galaxies that shouldn't have had enough time to exist yet, fully formed, unexpectedly massive, and showing up again and again in numbers nobody had predicted. We've had a visitor arrive from another star system entirely, tumble past us for a few short months, defy easy explanation, and vanish back into interstellar space, almost certainly forever. We asked 70 years ago, and continuing right up through today, where everybody else in this vast universe might actually be, and we're still waiting on an answer that has never quite arrived, apart from one unexplained 72-second signal in 1977 that matched what we'd hoped an answer might sound like, and then went silent forever. We found planets where it rains liquid metal, worlds that may hide diamond at their core, atmospheres torn apart by winds faster than anything Earth has ever produced, and, not far away in cosmic terms, an entire family of 7 Earth-sized worlds huddled close around one small, dim star, 3 of them sitting right inside the zone where liquid water could theoretically exist. We've confirmed the existence of stars so dense that a teaspoon of their material outweighs entire buildings, spinning faster than the human mind can naturally picture. We've proven, through Nobel Prize-winning experiments, that 2 particles can be linked in a way that defies ordinary common sense about distance and time, exactly as Einstein once complained it would, and exactly as he turned out to be wrong about. And we've sent 2 small machines, built decades ago with a fraction of the technology in the phone in your pocket, past the very edge of our sun's influence and out into the space between the stars, where they continue, even now, quietly reporting back. We've learned that our galaxy alone may host more starless, wandering rogue planets than it does actual stars, entire worlds drifting through the dark with no sun to call their own. Some of them, according to the James Webb Space Telescope, even forming their own miniature moons, despite having no star nearby to answer to. We've measured magnetic fields on dead, collapsed stars called magnetars, so extreme that a single flare can outshine our own sun's total output for 250,000 years, and traced at least some of the universe's most powerful explosions directly back to them. We watched one of the brightest, most famous stars in Earth's night sky, Betelgeuse, dim dramatically enough to spark worldwide headlines and worldwide anxiety, only to learn it had simply shed a piece of itself into space, rather than announcing the supernova everyone feared was coming. We've caught unexplained flashes of radio energy arriving from other galaxies entirely, some repeating on strict, clockwork schedules, one traced directly back to a magnetar inside our own Milky Way, and still, after nearly 2 decades of study, without any fully agreed-upon explanation for what's actually producing most of them. We sent a spacecraft to gently tap the surface of an asteroid, expecting solid rock, and watched it nearly sink straight through a surface that behaved more like a pit of plastic play balls than anything resembling stone, only to bring home a sample containing water, amino acids, and the basic chemical ingredients of life itself. We've found entire oceans of liquid water hidden under the frozen crusts of small, distant moons orbiting Saturn and Jupiter, kept warm not by any star, but by the simple, relentless flex of gravity itself, along with lakes of liquid methane on a moon of Saturn unlike anything found anywhere else in our solar system. We discovered that our own galaxy, along with 100,000 others, is being pulled at 600 kilometers every single second toward a gravitational anomaly known as the Great Attractor, sitting at the heart of a supercluster of galaxies so large It took until 2014 for anyone to properly map its true boundaries. We sent a small, piano-sized spacecraft to a distant, icy dwarf planet, once assumed to be a dead, frozen relic, and found mountains, glaciers, and a beating, actively churning nitrogen heart the size of Texas instead. And we followed a purely mathematical theory, built originally just to explain why our own universe looks so smooth and flat, all the way out to its logical endpoint, and found it strongly suggesting the existence of an effectively endless number of other universes, forever sitting just beyond anything we will likely ever be able to observe or confirm. We watched our newest space telescope stumble onto an entirely new category of object, almost by accident: small, strange, reddish points of light scattered across the early universe that briefly looked like they might upend cosmology itself, before more careful, deeper observations suggested at least some of them may be a genuinely new kind of object, gigantic, short-lived stars, marking the exact moment the universe's first supermassive black holes came into being. We chased indirect clues scattered across the frozen, distant edge of our own solar system, pointing toward a possible undiscovered ninth planet, tracked through the strangely aligned orbits of icy bodies nobody has ever actually seen influencing, an object some researchers are confident is really out there, and others suspect might not exist at all. We found a patch of the cosmic microwave background colder than physics comfortably explains, sitting in front of one of the largest voids ever mapped, without quite enough evidence to say for certain whether the two are truly connected or simply an extraordinary coincidence layered on top of another. We found an entirely separate, even larger void, much closer to home, a genuine gap in the structure of the universe large enough to swallow our own galaxy billions of times over, discovered completely by accident, while astronomers were simply trying to draw an ordinary map. And we sent a 0.5 millimeter long animal from Earth's own forests directly into the vacuum of space, stripped of protection, blasted with radiation no human being could survive for even a fraction of a second, and watched it come back to life, and even reproduce, once given nothing more than a drop of water. And we've watched a storm on Jupiter that astronomers have tracked continuously since the horse and buggy era, a storm once large enough to swallow 3 entire Earths, quietly and steadily shrink for well over a century, speeding up unexpectedly since 2012, changing its own shape, growing taller even as it narrows, for reasons nobody has yet been able to fully explain. None of this is speculation dressed up as fact. Every single discovery covered here came from peer-reviewed research, confirmed observations, and data collected by some of the most sophisticated instruments humanity has ever built. NASA, the Event Horizon Telescope Collaboration, LIGO, the European Southern Observatory, the James Webb Space Telescope, the Nobel Prize Committee itself, and teams of researchers spanning dozens of countries and institutions working over decades. And that's really the point worth sitting with as we wrap up here. This isn't a case of imagination outrunning the evidence. It's the opposite. The evidence itself, gathered carefully, checked repeatedly, confirmed independently by teams who often didn't even trust each other's early results until the data forced their hand, keeps outrunning what anyone originally expected to find. Every new instrument we build, every new method we develop, doesn't bring the universe into sharper, simpler focus the way you might expect. It reveals another layer of it we hadn't accounted for yet, another mystery sitting quietly behind the one we thought we'd just solved. The further into the cosmos we go, the stranger it gets, and based on everything we've just walked through together, there's no reason to think that pattern is anywhere close to finished. If this kind of deep dive into real, documented cosmic mysteries is something you want more of, make sure you're subscribed, because the universe isn't done surprising us, and neither are we. Somewhere out there tonight, another telescope is collecting another sliver of light that will end up rewriting some small piece of what we just walked through together. And there's a good chance we'll be back here explaining exactly what it means before too long.